Hello everyone, and in this video we're going to be talking about machine learning. This is going to be an introductory lecture just covering the theory, and in future videos we will be jumping into step-by-step real-world example problems to get into this stuff. But before we do that, we should have some foundational knowledge, and that's what we're going to get into. So at the very high level, machine learning is about taking data and trying to develop algorithms and models from that data. And so the algorithm is a method that we're using to learn some kind of pattern in the data. So if I gave you this chart right here and I had a bunch of different scatter plot points, you're going to be, if you think there's a linear relationship in this data, you're going to be applying a linear regression algorithm. And so in that case, the output of your algorithm is going to be a model, which is going to have the form y equals mx plus b that will describe, in this case, how the size of something is changing, what the expected price of that item will be. And so really kind of in this little example, the purpose of the machine learning model is to allow us to predict new stuff. So when I have some new object with some new size, I want to know what its price is, and this model will give me a way of figuring that out. Another important term before we jump too deep into it is features and targets. And so basically in this little example, our input is something that describes some object. And that input, in this case size, is going to be what a feature. So that feature describes, this could be something like the size of a rock, and how that size of the rock impacts the price of the rock, and the price is that target. So that's one area. As we move forward, there are some very exciting applications of machine learning. One of them that I really like has to do with healthcare and in radiology. People are using machine learning to look at MRI scans. And the thing that computers can do that humans can't is they can see far more shades of gray. The human eye can only detect about 250 shades of gray, but these computers and inside of these MRI files have many thousands of shades of gray in them. And so the computer is able to see patterns that a human eye never can, and it lets it come up with algorithms and models that are much more accurate at figuring out whether or not a MRI is cancerous or not. So big impacts there. Another area is fraud detection, where you don't need somebody to sit there and hard code what suspicious activity looks like. You can just give a bunch of financial transaction data to a model, and when some abnormality pops up, like a transaction happening in a different country or for something that someone doesn't typically buy, it's pretty obvious to a machine learning model that that is not consistent with other transactions from that given person. Another one is movie recommendations, and kind of grouping people into subsets. So if I know that you really like Adam Sandler comedies on Netflix, you might also like Bill Burr. And then another area would be something like autonomous vehicles, and this involves where the use of machine learning to make decisions based on real-time inputs. So on these cars that have cameras and lidars and GPS and radar systems, they have a ton of inputs coming into them, a ton of features coming into them, and they have to be able to figure out what to do. So if they detect a stop sign, your self-driving has to recognize that it needs to begin to slow the car down, apply the brakes. If it needs to make a left-hand turn to get to the direction you want to go, it needs to do that. So that's another very big area that people are currently pursuing. And so now what we're going to do is transition a little bit into the different types of machine learning. And so in one of these areas, it's called supervised learning. Supervised refers to the fact that the data set that we're training our machine learning model on is labeled. So in the case of the MRI scans that we had earlier, a labeled data set means that I'm giving the model a bunch of MRI files, and I'm giving it a column saying this one had cancer, this one was benign, and so on. So it already knows what the classes are, and I'm letting it figure out on its own how to classify that stuff. Another example would be if I gave you a list of emails and I said these emails were spam and these ones were legit. I've given you the labels ahead of time so that you can figure this out. And so supervised learning falls into that classification. process. So basically, we're trying to categorize our data. We're trying to assign a class to it. So when I give you an MRI file, you're going to tell me that this MRI file is a cancer type or it's a not cancer type. And regression is another supervised learning area. And an example of this is being able to predict the price of a house given a bunch of features such as the location, the income of the people around the house, the selling price of houses in that block, the number of bedrooms the house has, the number of bathrooms. So there's a bunch of different numerical features that we can give to describe a house. And the model is going to take those features and try to figure out what the price of that house will be. And you can use this in investing to figure out, what stuff has been priced fairly enough for you to make an offer on it. So that's supervised learning. Now we also have unsupervised learning. And so in this case, we're going to be learning from unlabeled data. And so, an example of this is going to be, if you're Amazon.com and you have access to terabytes of transactions on your site, you're going to take all these transactions and you're going to want to figure out, what groups of people here are you going to target some kind of ad campaign to. Another thing you do with unsupervised learning is dimensionality reduction. And so, the more data that comes into existence, the harder it becomes for computers to process this data. So being able to figure out which variables in a data set make the biggest impact on the target are really important. So an example of this would be humans have infinitely many features to describe them, but being able to figure out which features best describe whether or not you are most likely to buy a car the next year would be something where dimensionality reduction would come in to say, your income, the age of your current car, these types of features, whittling it down into saying what are the important data points here for us to care about are what really matters. Anomaly detection, again, we've touched on it. Has to do with, just based on all the transactions that we've seen this person make in the past, does this new transaction they're trying to make sense to us? If you're someone who's constantly bought groceries from a Safeway in Richmond, and then all of a sudden you are trying to buy a motorcycle in, Canada in a completely different city, that's probably a fraudulent transaction. So obviously, you can't hard code all the infinitely many ways this happens, but you need to be able to create something that can detect this, and that's where unsupervised learning comes in. Again, association rule learning for unsupervised learning. This has to do with, again, looking at, for example, a bunch of transactions and recognizing patterns in this behavior. So you might notice from your financial transactions that people who buy a lot of toothbrushes also buy toothpaste together. So if you are trying to optimize your store layout, you would probably want to put your toothbrush next to your toothpaste to get the most sales. And there's another area called reinforcement learning. And this is a little bit of a blend of the supervised learning, but basically what happens, and a good example of this is autonomous driving, is you will have a bunch of features that are fed to your model. And so you're going to observe the environment. It observes, so in this case, like pretend you had a Tesla, it's going to get a bunch of inputs from the cameras, the LiDAR, radar, GPS. And with all these inputs, it's going to have to make a decision. And so you've told your Tesla that you want to drive to the 7-Eleven down the street. And so based on the goal and its current environment, the model is going to make a decision to turn right at this stop sign. And so these are the types of decisions that they make, and they will involve some kind of feedback. So the reward could be something like a distance closer to your target. So if I'm trying to go to 7-Eleven, I'm now closer to 7-Eleven than I was in the last second. But you could also have penalties such as rolling a stop sign, failing to stop at the stop sign, driving on the wrong side of the road. So failing these traffic rules would penalize the system. And so what happens during reinforcement learning is you're going to be adjusting your policy based on the feedback that you're getting. The rewards and the punishments that you're getting along the journey are going to affect how the model is changing its parameters. And it's going to have to do this in pretty real time. And so this kind of brings us on to this next topic, which is the different types of data to expect. And so when we are dealing with data that's constantly coming into us continuously in some kind of stream, so again, coming back to the self-driving car, the camera feed is constantly updating. The frames per second is 30. So 30 times a second, you have a new picture that your model has to look at to figure out if it's in the right lane, if that's a stop sign, if that's a kid running across the street, if there's a car trying to overtake. And so there's a bunch of different things that the model is having to constantly figure out in real time to make a decision. And so this is what online learning is referring to. Another example is stuff like stock prices, because during the day, there's going to be more information available to you, such as a company's earning report that just gets released, or some kind of press release that dramatically changes the market sentiment on a company. Like if they just lost FDA approval for something, it's going to have to change. That new data is going to have to update the model to recognize the fact that the target price of this company is probably lower, and so that's what online learning involves. Then we have another thing called out of core learning, and this is where your data is just too big to fit into memory, so you need to break it down into smaller chunks to process it. An example of this would be genomic data sets or climate models, where the amount of data, the volume, its size is just too big for a computer to process at a given moment. And so it requires different techniques to be able to train those models and use them. And then we're going to talk about model parameters and hyperparameters. So parameters are what your model is tuning while it's being trained. So in the case of that y equals mx plus b graph that we looked at on the very first slide, those parameters, your model is basically trying to figure out what is the appropriate slope and y-intercept to have in that graph in order to get the best fit line it can to minimize the loss or the error from the model that it has. So those parameters are what's being tuned. And then we have things like hyperparameters, and these are the things that the machine learning engineer is responsible for specifying, and these have to do with things like learning rates or the number of hidden layers you have in a convolutional neural network. So these are things that are basically hard points that are dictated by a machine learning engineer. And so these are important terms to keep in mind as we're doing more projects. And I also want to talk about some of the challenges that people face with machine learning these days. Number one has to do with insufficient training data. So obviously, the more data you're able to give a model, the more stuff it'll have to be able to learn from. And so it's very similar to a kid trying to learn Spanish. If you just gave the kid a pamphlet in Spanish, they have nowhere near enough data to be able to speak fluently to other people in Spanish. They need to have a lot of textbooks and Gabriel Garcia Marquez available to them to really be able to read and also be able to talk to other people in Spanish. So you need a lot of data to train a model. Another thing is non-representative training data. So if you're trying to teach a kid Spanish, why would you go out and buy a German dictionary for them? That's not going to help them. They're trying to do something entirely different. So you need to make sure that your training data for your model is what you're actually trying to train your model on. Another thing like this is poor quality data. So the data itself, even though you might have bought a big textbook and it's all in Spanish, if the textbook has a bunch of typos and noise and torn pages, it's going to create issues for your model to be able to learn from it. Another thing is irrelevant features. So again, even if my textbook is Spanish, if I have a bunch of calculus sections in it, it's not helpful to have for the model. So to be a good machine learning engineer and to create models that are able to generalize well, and that is our ultimate goal, we want to make sure that we have relevant features in our training data set. Another thing that happens is overfitting of a model. And so the issue that happens in this case is where your underlying data will have some relationship to it. So if you expect to see a linear relationship between the price of a house and the number of rooms that it has, and you are trying to fit a 20th degree polynomial to all these data points, you're going to end up with a problem called overfitting, where you'll have a very low R squared value because the 20th degree polynomial has a bunch of different degrees of freedom available to it, but when it tries to generalize stuff, this 20th degree polynomial will be so ridiculous at its outliers that it's going to come up with ridiculous predictions. Similarly, we have underfitting, and that is a problem where your data might be in the shape of a parabolic curve. And in that case, you would expect to, by trying to fit a linear model to that, it's going to not generalize well again in the long run. And so that's a key thing to make note of for the person who is trying to be a machine learning engineer, to figure out really you have to intuitively have a good understanding of your data before you jump into it and start just throwing models at it. And so in terms of how you have solutions to these problems, it's really coming down to the machine learning engineer to balance the simplicity of your model with generalization. So we want to be able to generalize well enough from a simple model, and that is far more challenging, easier said than done. And so, the ways we do this, we need to make sure we have a test set that is accurate, and it's a good generalization of the training data as well, because when you pick a test set, typically test sets will be about 20% of your total data set. And if that 20% you pick has bias in it relative to your test or your training data set, then your model is going to change its parameters in ways that will give you poor performance. And again, how you split this data is extremely important. And this is where we have to break stuff down into a training set, a validation set, and a test set. The purpose of the test set is to measure how well that model generalizes stuff. The purpose of the training set is to determine what the model parameters should be. And then the purpose of that validation set is for the machine learning engineer themselves to try a bunch of different hyperparameters to see what yields the best generalization performance. So that could be something like changing the learning rate to see how different learning rates are able to get you better generalization performance in the long run. And again, just kind of coming back to it, once you start splitting your data, you are running the risk of introducing bias into your data sets. An example of this could be if in your overall data set you have a ratio of 50-50 males to females, but in your training set, because it's only 20%, if you had 70% female and 30% males, well, now you've got a pretty skewed training set. So these are things to really think about and be careful when you are inside of a project with this stuff. So I'm going to wrap things up with that. But in the next video, we're going to jump into actually building these models and testing them out and playing around with them. And so stay tuned for that. Thank you all for watching. Let me know if you have any questions, and be well.